Let's talk about what's on the quiz. Let's say you have an object and it's moving to the right, but you want it to go around the center of a circle. You need a force that's pointed towards the center. We call it a centripetal force, towards the center. That's what it means. The object makes the turn, and so must the force. The force will be perpendicular to the velocity. The speed does not change, but we still say there's a change in velocity. Because velocities are vectors, the change in velocity is not due to a change in magnitude, it's due to a change in direction. The velocity was this way, now it's that way. There's only one way you can change the motion of an object, and that is with a force. And we all know a force is equal to a mass times an acceleration. If this force is towards the center, the acceleration is towards the center. Think of the force as pushing the velocity around toward the center. The acceleration is a change in velocity over change in time, but like we said, it's not due to increase in speed. That's due to a change in direction, which is equal to v squared over r. We derive that using similar triangles. And when you use this formula, you always have to identify what causes the FC. If we have a mass on a string and it's going around in a circle, we would say the tension causes the FC. We could use these numbers, plug everything in, we get 6.25 newtons. And from v squared over r, we get a centripetal acceleration of 125 meters per second squared. Just to prove this, let's see what happens when the object rotates 5 degrees. We put these two velocity vectors tail to tail, and then we can see that the change in velocity is towards the center. Now, if we say that's 5 degrees, we can calculate the change in velocity just using trigonometry. This is an isosceles triangle. We get 0.8724 meters per second. Now we'll see how long it takes to travel this distance. For a small angle, we'll approximate this to be a straight line. If I know the distance and I know the velocity, I can get the time. I get the distance by doing an isosceles triangle and solving for the distance. And here's the time it takes to go from here to here. Well, that's the same time it's going to take for this change in velocity to occur. What's a change in velocity over the change in time? An acceleration. If the change is towards the center, the acceleration is towards the center. So we take the change in velocity found from this triangle and divide by the time from this triangle. Change in velocity over the change in time, hey, we get 125 meters per second squared. That's what we got using this formula. So yeah, this formula was derived by doing these triangles, and it works. Let's look at a first problem with a mass on a string in a horizontal circle where the string is horizontal. It's what we did in lab. Now we're making an approximation that the string is horizontal. In actuality, it has to hang down a little bit so that the tension in the string can generate a y component. That y component stops the weight from falling. What's left is the tension in the x direction, producing the FC. Now, if we go fast enough, this string will start to become more and more horizontal. You saw that at home. What does that tell us? As the string becomes more horizontal, the tension increases to the point where the tension in the y direction is very small compared to this. It's the tension in the x direction that is nearly equal to the tension in the string. Well, if we approximate these two things to be equal, we'll just say the string is horizontal, and it makes the problem easy. Well, it was the first lab, so we said let's approximate the string to be horizontal to make it easy. The tension is what causes the FC. Now, let's say the mass completes 12 rotations in 5.2 seconds, given all this information. Find the tension in the string. Pause the video, try it out. Ignoring any sag, we can say the tension is the FC. FC is mv squared over r. The velocity is the distance over time. 2 pi r is the circumference, so that's the distance it travels per rotation times 12 rotations in this amount of time. The velocity is 8.7 meters per second. R is 0.6 meters. The mass is 0.04 kilograms. And we get 5.04 newtons. That would be about the maximum on the green spring scale that we used. So here we have an answer for part A. Now, what if we said we were going to spin faster and do the 12 rotations in 2.6 seconds? Could you find T? Mass is the same, radius is the same. What happened to the velocity? Well, you can go do all the math and plug in all the numbers again, or you could say, hey, we cut the time in half. That's going to double the velocity, but the velocity is squared, so it should make the tension 4 times bigger, and that's 20.16 newtons. Okay, let's take a look at our second lab. We had an 80-gram mass on a string 120 centimeters long going in a vertical circle. What if this mass completed 3 rotations in 4 seconds? Can you find the tension in the string at the top and at the bottom? Now remember, in this lab, we assumed that the velocity is constant. That's not true. That's okay. It's just an approximation. So pause the video and see if you can find these two now. First thing you want to do is draw a free body diagram. At the bottom, mg is down, tension is up. At the top, both the tension and mg are down. They're pointing towards the center. So what's producing the centripetal force at the top? It's going to be both of them, T plus mg. And we know that the FC is mv squared over r. Well, how do you get v? Distance over time. We get 5.65 meters per second. Plugging in all the values, we can now solve for T. We get 1.35 newtons for the tension at the top. So that's the tension at the top. What about the tension at the bottom? We look at the free body diagram. What's keeping this thing in the circle? It's the tension, and the mg is going the wrong way. So it's T minus mg. It's still going to be the same velocity for our approximation, 5.65 meters per second. Plug in all your numbers, and we get a tension of 2.92 newtons. And look at that. The tension is bigger at the bottom than at the top. Well, that makes sense. When you're swinging it vertically, you have to pull harder to fight gravity. At the bottom, when you're at the top, gravity's helping you. You don't have to pull as hard. Okay, that's good for part A. Okay, that's good for part A. Well, how about part B? How slow can you go and still maintain a circle? The critical point will be at the top. That's where we have the tension and the mg both contributing to the FC. But if we went slower, the tension would be smaller. And if we go slower, well, the tension will go to 0, and it'll just be the force of gravity keeping this thing in the circle. Any slower than that, and the force of gravity will be too big, and it'll curve in too tight, and the string will start to collapse. Well, then we can say that the FC is produced solely by gravity. FC is mv squared over r. Masses cancel. And we can say v equals the square root of rg. That's a minimum. That's as slow as you can go and maintain the circle. Plug in your values, and you get 3.43 meters per second. If you tried doing that with the lab, you'd get to the point where the spring scale would read 0. How about the conical pendulum lab? So we have a string, 70 centimeters long, center to the center. We're going to have 200 grams here swinging around in a horizontal circle over the meter stick. Why did we do it over the meter stick? So we can measure the radius. If you swing this out far enough, it'll be right over the ends, and then middle will be 50, and so the radius will be 50 centimeters. Let's find the velocity of the mass. Let's get it theoretically and experimentally. Now pause the video and try to find it theoretically. First thing we'll do is draw a free body diagram. We have 2 forces acting on that mass. That's it. We're going to break the tension in the rope up into 2 components. The y component has to equal mg because it's not accelerating up or down. They have to be equal. The x component, therefore, is what's causing the FC. There is an acceleration towards the center of the circle. Well, we know FC is mv squared over r. We're looking for v. Well, if I can get that angle, I can say tx over mg is equal to tangent theta. Now I can replace tx. Hey, look at that. The masses cancel out. But how do I get theta? From the geometry of the problem. You've got the length is 70, you got the radius is 50 centimeters, you get 45.6 degrees. That's the angle up here, which is equal to this angle. Plug in all your values and you get 2.24 meters per second. Well now, that's our theoretical. How do we get it experimentally? We watched it go round and round and you timed it with a stopwatch. Would it make any sense to do it for one rotation? No. You'd probably want to do it for 3 or 4. So let's say it went 4 rotations in 5.8 seconds. Could you calculate an experimental velocity? Well, that's a distance over time. Circumference times the number of rotations divided by the time. We get an experimental velocity of 2.17 meters per second, which is reasonable that we did in our lab. Okay, that's great for part A. How about part B? Find the theoretical tension. Better pause the video and try it. We go right back to the free body diagram. If you know your FC theoretically using the theoretical velocity, hard to believe, but we got 1 Newton. If you know TX and you know the angle, you can get the tension. Just use sine and you get 1.40 newtons. And you could check that using mg. That's got to be 0.98 newtons. Use that angle. Go calculate the tension. You're using cosine now, and you get the same thing. Of course, the tension experimentally could be found by grabbing the spring scale and reading it. Okay, we did this in lab on video. You got a turntable, you put a rubber stopper on it, and you rotate it faster and faster and faster until all of a sudden the rubber stopper slides off. At that point, the turntable is going to maintain a constant rate of rotation and it completes 3 rotations in 2.5 seconds. Find mu s. Again, pause the video, try the problem. Again, we start with a free body diagram. Weight going down, normal force going up. The question is, what's producing an FC? Has to be a force of friction. So if we start with the force of friction is producing the FC, we've reached the maximum static friction just as this thing breaks free. So it's mu s times mg. That's the normal force. FC is mv squared over r. We can get v from this information. We get 1.13 meters per second. Well, boy, the masses cancel. Plug in all your values. Hey, we get 0.867. That's great for part A. Okay, we put the rubber stopper on the turntable, and we start to tilt the turntable slowly until we reach an angle of 38 degrees, at which point the rubber stopper starts to slide off. What's the mu s? Hey, you can just get this by doing tan theta. You get 0.781. Okay, reasonably close. I think in the video lab, we had a lot more error than this. It's very easy to get error because these things get hung up on a little patch of rough stuff on the turntable. When you tilt it, any vibrations, when you rotate it, any vibrations, set it off early. Orbital velocity, let's try one of those. Well, at astronomy night, we saw a satellite. Let's just pretend it was 400 kilometers above the Earth. We know the radius of the Earth. We know the mass of the Earth. We have to find the orbital velocity. Now pause the video and try it yourself. Again, with the free body diagram, a force of gravity is what's causing the FC. So if I start with that, well, that's the object going in the circle, and that mass is the mass of the satellite. This is Newton's universal law of gravitation producing the force of gravity all the way out there. That's the mass of the satellite. They cancel. So does R. And here we have the formula for orbital velocity. Well, we've got the mass of the Earth, we've got the radius of the Earth, but that's a lowercase r. That's got to be the radius from the center to center. That's the orbital radius. That's the radius of the Earth plus the height. and you get 7,681 meters per second. That's great for part A. Let's find the period. In other words, how long will it take for it to come all the way back around? We know velocity is distance per time. And when that distance is one circumference, the time becomes a special time. It's the period. We know the radius. We know the velocity. That's 5,530 seconds. That's 1 hour, 32 minutes, 10 seconds. Remarkably fast, don't you think, to go around the Earth? Could we get a period experimental for this? Sure. If we waited an hour and a half, we should see the satellite again. But it won't be in the same place because the Earth will have rotated a little over 20 degrees. Lots of applications for all of this stuff. We have space station problems with artificial gravity, roller coasters, bank track problems. All of this stuff comes from the same problems that we've been doing. Well, you can always watch more videos through the chapter notes and the worksheets. I will tell you that a lot of the stuff on Worksheet 2 is tricky. Most of that stuff, it's hard. You're not going to see the hardest stuff on all of these problems. You might see a couple of hard ones. Good luck, everybody.